All right, let's plug into one of the most foundational concepts in all of electrical engineering, the epic story of AC versus DC. And trust me, this is way more than just about what kind of charger your phone uses. It's a story of genius, rivalry, and an invention that literally powers our entire modern world.
So here's our game plan. We're going to start with that historic rivalry, the War of the Currents. Then we'll get into the nitty-gritty of how these currents actually work. We'll find out why our power grid went one way, and then see how both AC and DC have to work together today. And finally, we'll wrap up with some crucial insights from an engineer's point of view.
And what a battle it was. Seriously, this isn't just dry physics. It's a story packed with innovation, absolutely fierce ambition, and a huge public showdown between two of the most brilliant minds of the 19th century, Thomas Edison and Nikola Tesla.
Okay, so picture this. It's the late 1880s. Thomas Edison is the king, and he's all in on direct current, or DC. But it had a huge problem. You couldn't really send it very far without losing a ton of power. Then comes Nikola Tesla, and he's got this amazing alternating current, or AC system that could solve that problem. This kicked off a massive public feud. Edison even went around publicly electrocuting animals just to try and prove that AC was too dangerous. But in the end, you just couldn't argue with the practical advantages. AC won the contracts for both the Chicago World's Fair and the absolutely groundbreaking Niagara Falls power plant, and that pretty much sealed the deal. So, what was the big technical difference that sparked this whole thing? Let's break down how these two types of current actually flow, from the absolute basics to the complex systems we use every day. You know, it really all boils down to the direction the electrons are moving. DC is just a steady, one-way street. It's simple, it's predictable. AC, on the other hand, is constantly changing its mind, flipping its direction back and forth, over and over, in a perfect rhythm. And if you were to look at it on a graph, DC is as simple as it gets, just a flat, straight line. This steady, predictable flow is exactly what you want for things like batteries, solar panels, and all the delicate little circuits inside your electronics. AC, on the other hand, gives us this beautiful, smooth, oscillating sine wave. Now, the number of times it completes one full back-and-forth cycle per second, well, that's its frequency. Here in the US, our grid runs at 60 Hertz. That means the current is completely reversing its direction 60 times every single second. It's kind of mind-blowing when you stop and think about it.
Now this brings us to a really critical idea for AC. How do we actually measure its power? We talk about its RMS value, which you can think of as its effective or its DC equivalent voltage. But look at that sine wave. It actually reaches a peak that's much, much higher. So a standard 220-volt AC line is actually hitting a peak of 311 volts during each cycle. Keep that in mind because it's going to be incredibly important when we talk about safety later on.
Okay, so if DC is so much simpler and more stable, why in the world did we choose the complex, oscillating AC to be the standard for our entire power grid? Well, the answer comes down to one single, game-changing invention: the transformer. This beautifully simple device can effortlessly and efficiently step up AC voltage to crazy high levels for long-distance travel, and then step it down to safe levels for us to use in our homes. This was AC's superpower. It was the one thing DC technology at the time just couldn't do well.
And the magic word here is efficiency. See, by jacking up the voltage, you can send the exact same amount of power using a much lower current. And since the energy you lose as heat in the wires is tied directly to the current, well, you cut down on waste dramatically over long distances. This was the economic knockout punch that made massive, centralized power plants possible.
But here's the twist. The war isn't really over. It's more like a truce. The reality is, today we live in a world that completely depends on a seamless hybrid of both systems working together perfectly. And this right here illustrates the modern divide perfectly. AC is the heavy lifter, the bulk carrier that gets delivered to our homes to power big appliances and motors. But almost all of our modern gadgets, your phone, your laptop, LEDs, even your electric car, they all run on the steady, calm power of DC. And that's exactly why every single one of those devices has that little power brick, right? That block is a converter. Its only job is to turn the wall's AC into the DC your device actually needs. And in a totally fascinating turn of events, DC is making a huge comeback in the exact area it first lost: long-distance transmission. With modern power electronics, we can now create high-voltage DC, or HVDC,
which turns out to be even more efficient than AC for moving enormous amounts of power over hundreds or thousands of miles, like through those massive undersea cables that connect entire countries.
All right, for all the students and engineers watching, this is where we get into the really important stuff. Understanding the theory is one thing, but you have to appreciate the practical and sometimes pretty dangerous details that pop up in the real world.
Now, look at these numbers really carefully. It takes a much smaller amount of standard 50 or 60 Hz AC to cause that terrifying can't-let-go effect and the lethal heart condition, ventricular fibrillation. Why? Because that specific frequency messes directly with our body's own electrical nervous system, which makes it uniquely dangerous.
So this leads us to a really critical question, one that anyone working near electricity needs to know the answer to. If you have the same effective voltage, which one is a bigger threat?
And the answer is a definitive yes. Remember our chat about RMS versus peak voltage? That 220-volt AC line is hitting a peak of 311 volts 60 times every second. That higher peak voltage is going to deliver a much more intense jolt during each cycle than the steady 220 volts you'd get from a DC source.
Here's another key concept for engineers, the skin effect. It's one of those weird but really important quirks of physics. In an AC circuit, the electricity doesn't actually use the whole wire. It tends to crowd toward the outer surface, or the skin of the conductor. And this effect gets much worse at higher frequencies and in bigger wires. Now, why does that matter? Because the current is being squeezed into a smaller area, it's like trying to force the same amount of water through a skinnier pipe. The resistance goes up. That means more heat and more wasted energy. If you're designing high-frequency systems, you absolutely have to account for the skin effect to keep things from overheating and to maintain efficiency.
So let's wrap this all up. What are the key takeaways? First, AC won the grid war, plain and simple, because of the transformer. Second, DC is absolutely essential. It powers all our modern electronics and renewable energy sources. Third, from a safety standpoint, standard AC is more dangerous than DC at the same voltage rating. And finally, engineers have to deal with complex real-world issues like the skin effect in their designs. And that leaves us with a final, really interesting question to think about. As our world moves more and more toward technologies that are naturally DC, like solar panels, batteries, and electric cars, are we about to see the balance of power shift? The century-old war of the currents might not be over at all. We could be heading into a brand new chapter. What do you think the grid of the future is going to look like?